And now we will make some practical examples on pressure vessel design, particularly on the design of opening reinforcement. Well, we have here a cylindrical vessel. The vessel is horizontal. It's composed by a cylindrical shell with two toruspherical ends. Now we want to add a nozzle on the cylinder. So we start, first of all, let's look a little bit at the characteristics of this vessel. We take the shell and for the design conditions, we see that the internal pressure is 1.5 megapascal, that means 15 bar. The temperature is 150 degrees. The joint efficiency is 0.85 of the shell, of course. The corrosion allowance is 1 millimeter. There is no problem of plate tolerance because, according to ASME VIII Division 1 and also to Division 2, the plate tolerance must not be taken into account if the tolerance is less than the smaller value between 0.3 millimeter and 6% of the thickness. In our case, as all ASTM materials, the tolerance is 0.25 millimeters, so it has not to be taken into account. The thickness is 18 millimeter. The diameter of the shell is 2.5 meters, and the length is 6 meters. So, okay, now we want to add a nozzle on this cylindrical shell. Let's take the nozzle here. The material has been automatically selected because in the specification we had specified that the vessel has to be made of carbon steel. We have an SA 106 grade B, and therefore that's a pipe material. The nozzle is inserted into the shell, so it's a thin nozzle. The height, say we can select a height of the nozzle of 400 millimeter. The nozzle thickness, we take the nozzle from the database. So take a diameter 14 inches, for example, 14 inches with an extra strong pipe. The thickness of the extra strong pipe is 12.7 millimeter. And we have to choose something, for example, the welds. The weld, leg of nozzle to wall fillet weld, say, for example, 13 millimeter. At this point, what is still missing? It's missing line offset outside shell limits. So, okay, we have still to decide where to put this nozzle. This nozzle, so position, is at the top of the shell, so the north is 0. Offset from shell border, say we keep it at 1 meter from the edge of the shell. We see that there is something wrong. We want to see it better. We look at the preliminary report, but the same thing was written here. The area, the minimum required area is 4,593, and we have only 1,706. So the correct design procedure is, first of all, we have to try to use the nozzle thickness. So if a 12.7 millimeter thickness is not sufficient, maybe it is possible to increase the thickness. So we go here in the geometry, pipe database. We open the database. There is not a double extra strong on this database. The double extra strong is considered up to 12 inches nozzle. Now we can try to use, for example, a schedule 80 nozzle, 19.05, maybe also something more, 120. Of course, this is not a very easy pipe to find on the market. Then we have always to think how much of this pipe we will use, because the standard length and generally is 6 meters. So we need 400 millimeter only, unless we have other nozzle. This is not reasonable. So, but in any case, we can look it here or also here. The required area is not achieved. So we come back, let's come back to the original thickness. We had selected 12.7, and we have the option either to add a reinforcing pad or to make a self-reinforcing nozzle. So the first idea, let's try to add a reinforcing pad. Reinforcing pad based on the reference dimension. We take the pad width. The pad thickness is equal to the thickness of the shell, 18. The pad width is, say, 120 millimeter. Under tolerance is not considered. The pad material is the same material of the shell. Then we have still to add something. Also, the leg of pad to wall weld. Say there is another weld. We have to consider this weld, and this time you see that everything is okay. How much is it okay? The area required is 4,593. We have 6,409. Okay, maybe 120 as length. We come back to the pad characteristic. Maybe also with 100 could be adequate, of course. But I mean, this width, there is no meaning in selecting a lower width, because the cost of the nozzle is not the cost of the material, it's mainly the cost of man hours. So let's keep this 100 millimeter, and we are satisfied with this design. Well, it is worthwhile checking if a reinforcement of a 14-inch nozzle could be better achieved using, for example, a long welding neck flange. So we could try to make another nozzle, also with a diameter of 14 inches, but using a long welding neck flange. First of all, we must decide something. Okay, the material has already been chosen by the software. The material is a carbon steel material for forgings, of course. And then the type of connection is satin. The length, maybe we can choose a length which is a little bit more, because we have now to take into account also the flange length, say 400 millimeter. Flange thickness, it doesn't matter, because we will select a standard nozzle, a standard flange. Standard flange, select, for example, let's take a series 300 flange, 14 inches, of course, and then disable bolts and gasket validation. Well, this is interesting because we don't want to check the flange itself. We want simply to check the opening reinforcement. So we put a tick here. Then we have to decide where to place this second nozzle. Angular offset 0, offset from shell border, say at 3 meters from shell border. Nozzle position radial, welds, of course, the length of nozzle to weld, and then the fillet weld area. Say if you take 15 millimeter here, then considering that there are 2 of these welds, the fillet weld area should be 225. But okay, we have already some kind of answer from the program. The answer is the following: required 4,894 and the actual 4,107. It is still not sufficient. Of course, we could take a difficult decision, for example, when we come back to geometry, we can try to make a self-reinforcing nozzle, increasing the thickness here, but so we lose the advantage of using a standard component like a long welding neck flange. We need a special flange. A special flange costs a lot of money because it must be made especially for us. So we do not want this solution, but we still may have the doubt if there is another possibility. The possibility essential, maybe is under essential here. No, it's not here, it is under general, and this is the possibility. Use Section 8 Division 2 rules, code case 2695. Now it's not anymore a code case, because there is in edition 19 there is a specific appendix 46, in which it is written that we are able to use all the rules of Division 2, provided we use the nominal design stresses of Division 1. So let's see if this is possible. Okay, we put the tick here, and you see the opening is reinforced now. So, okay, there could be the idea of doing the same thing with the other opening. So we accept this, okay, and then we go back to this opening to see if using the same trick gives maybe the possibility to eliminate the reinforcing pad. So let's open this again, and under General, there is the use of code case 95. Okay, the only problem seems to be the size of this weld, but I mean, not the only problem. The problem is that we wanted to eliminate the pad, so let's take out the pad, and even if we can maybe change the weld size here, but this was not the problem. The problem is really that the opening is not reinforcement. If we want to know a little bit the philosophy of this, we look at the preliminary report. In the preliminary report, we will see that the stress is too high. So the primary stress in this case is too high, because the philosophy of Division 2 is based on the following. It takes into account an area of reinforcement, and in this area a stress is calculated. Its stress is considered a primary local. A primary local should be always lower than 1.5 S, the allowable stress, but unfortunately this is not the case, so there is nothing to do. We leave our pad, we leave our reinforcing pad, and okay, changing the weld size also. Welds 16 millimeter, okay, we could always use the method of Division 2, but in this case the stress is acceptable, but there is no reason to use the method of Division 2, so let's take out the tick. The opening is always reinforced, and we'll leave it like that. Okay, now let's see, just to have an idea, what is the weight of a vessel like this with these two openings. Item properties. The weight of this vessel is net weight 8,750 kilograms. Well, now we close this, save item. Side item is saved, and then we close this item, and we open another item, this one. This was the same vessel, except that the calculation was made only for the cylindrical shell, and this is calculated to EN 13445 3 issue 5, the latest available revision. So let's look a little bit at the shell. The shell design conditions are always the same as for the ASME vessel. 150 degrees centigrade, design temperature, then design pressure 1.5 megapascal. We have a joint efficiency of 0.85, we have a corrosion allowance of 1 millimeter, and we have also a tolerance. In this case, in the ASME calculation is not required, but for EN, we have to consider this 0.3 millimeter tolerance. Now, look at the preliminary report. The preliminary report says the minimum required thickness is 12.43, and in fact, in the geometry, we have used 13 millimeters. Note the difference with the ASME vessel. The ASME vessel had a thickness of 18 millimeters, much more than 13. Diameter is always the same, the length is always the same. So we say OK, and now we want to add a nozzle, or a 14-inch nozzle, like we have made with the ASME vessel. The material, carbon steel, has been automatically selected, P265GH. We take the nozzle from the pipe database, as in the other case, we select a 14-inch nozzle, we select the extra strong thickness, the nozzle height is 400 millimeter, and then we have to establish the position. We want to put it, say, at 1 meter from the edge, and then we have to, opening not reinforcement, it's automatically made the calculation, and unfortunately we are very far from the reinforcing this opening. So in this case, what it is important is the reactive force and the pressure load. The pressure load, so is 673,000 Newton, while the reactive force is only 499. So, as in the other case, we can try to increase the thickness. So we go back to the geometry, to the pipe database. The pipe database, we try, there is no double extra strong pipe, so we try with, say, schedule 80. But even with the schedule 80, as you can see here, we are at 585,000 against 676,000. So nothing to do. So the only solution that we can think possible, so there are other solutions, or either the forging or the reinforcing pad. Let's first check with the reinforcing pad. So we add a reinforcing pad. We have not on the outside diameter, but on the width. Say the width is 100 millimeter. The thickness is the same thickness of the shell, 13. Paid material is the same material of the shell, and now everything is okay. There is something, no, we have to consider the fillet weld area. The fillet weld area is just an area, it's not a distance, say for say 10 millimeter, so 100, considering both welds, and you see the calculation here. We have now the transverse check, which is important. the transverse check, we are the reactive force is 838 and the pressure load is 347. So everything is okay. Now what we want to see if it is possible to use a long welding neck. So we take a long welding neck. No, sorry, I have made a mistake, because in this way I would have placed the long welding neck on this nozzle. So I have to select first the shell and then take the long welding neck. Long welding neck, which has now a forging material. I have to select first of all the length, 500 millimeter, like in the other case. Then I have to go to the standard flange. Standard flange is now, I have the selection between two possible EN flange series, but this is similar to DIN. We take EN 1759 because this is the same as the ASME flanges, so they are the same classes. So I take class 300 and then I take the 14-inch flange, this one. Warning, inside diameter shall be specified by the user. Please check that the value of B has been inserted before selecting a standard flange. Okay, so the inside diameter for this flange is considering that the outside diameter is 356.6. The thickness was of the standard pipe was 12.7 times 2 means 25.4. Then I subtract this 330. So the inside diameter is 330. I have to go here in the geometry. Inside diameter 330. Now I can go again the standard flange. I select the EN 1755 and then the class 300, 14 inches. This is the flange. Now everything seems to go okay. No, I have to disable bolts and gasket validation because I am not interested in this. So I am interested only in the line offset outside limits. Okay, that means it has placed the nozzle at the beginning of the shell because I have forgotten to specify the distance from this edge, from the edge of the shell. So I have to go to position and say 3 meters. Okay, 3 meters. Now everything seems to be okay except for a yellow warning. Let's check what is this yellow warning. Selected thickness is outside the material size limits. So this is normal with the EN standards because the EN standards consider different characteristics with different thicknesses. So the material which has been automatically selected is the one with the minimum thickness. I have to go to here to general. I open the database. I see that for this material P280GH there are 3 classes of thickness. I take the highest classes, and you see that the yellow warning has disappeared. So, differently from what happens with the ASME code, with EN it is possible to make a reinforcement with a long welding neck flange. So I'd say okay. and I have my second flange here. If I want to make a comparison of weight, the other vessel has the same dimensions of the cylindrical shell, but it has also the toruspherical end. So I have to add the toruspherical ends here. So I select the shell, toruspherical head, cylindrical shell left side, OK. So what happens now? There is something wrong in this end. Well, of course it has selected the same thickness as the shell, while here a higher thickness is required. But let's see something better, a little bit better, the problem, because first of all it has taken the wrong type of end. I don't want a decimal end. I want a 2 to 1 end. So it means an end with a 0.8 the diameter. The large radius is 0.8 the diameter, so it's 2000. And then small radius, the small radius should be 0.154 times the diameter, so this means 385 millimeter, 385. But then there is a further problem. The further problem is the following. Okay, now it seems that everything is okay, but it is not true, because I have forgotten one thing. Under general here, under design conditions, sorry, I have to correct this joint efficiency. The joint efficiency is not 0.85. The joint efficiency should be 0.85 if the end is made of 2 pieces or more, but the end is with this diameter can be taken from a single plate. So I have to use 1 here. I have to put 1 here, and I don't want to apply this one to every component, so I want just for the end. And then let me check the preliminary report. Before looking at the preliminary report, there is something more in the geometry. I have to consider the straight flange. The straight flange should have a length at least of 80 millimeter. Then in the preliminary report, the minimum thickness of this end is 11 point, minimum required thickness is 11.7. So the 12 millimeter is okay, 12 here, and also for the flange, for the skirt, sorry, is 12 millimeter. Everything seems to be okay now, but there is a yellow warning. Let me check what is this yellow warning. Okay, this is the problem that I have already mentioned before, the fact that the actual elongation is 20%, and therefore a heat treatment is required. So I say okay. Now I have to add an equal end from the other side. Copy toruspherical head on 1. I copy from the opposite side. I don't want to edit it. If it is exactly equal, for me it's okay. Now this is my vessel. I want just to check the weight. The weight, component item properties. You remember the weight of the other one was 8,750. This one is 6,585. So you see that having made the design according to ASME VIII Division 1 and the design according to the harmonized standard, using harmonized materials, you see that there is an important difference. Okay, I have finished. Thank you for your attention.